Back. Today we're going to do question number 12 of this series. So today we're looking at the question container with most water. So given an array of height of length and array height of length, and there are n vertical lines drawn such that two endpoints of the ith line are I0 and I height I. Okay. So we're given an array like this, and then we are supposed to find two lines that together with the x-axis forms a container, such as container forms the most water. Okay, cool. Yeah, I think I understand the question. So we have a height here of arrays of all these various heights. So this is 1, this is 8, this is 6, 2, and so on and so forth. And then we need to find the best, largest amount of area a container can store. So we're looking at this again. We have height 1, 1, height dot length is equals to n. N is between height. Okay, this array has n elements. N is between 2 to this. Okay, height can be a very large number. Okay, so straight up when we're looking at this question, I would suppose we would do a two-pointer method. Again, looking at this particular method, we probably have to look at an array, right? We probably have to look at two pointers here that are forming the rectangle, and when we're surrounding the rectangle, we have to look at which number is the larger number, right? So for example, when we look at this question, we're looking at I and j, and then we have I as the, so we compare I and j, right? Versus height j, and then if the smaller one will form the height, right? The length will be j minus I, right? And then essentially, are there any space requirements? Nope. So we will just traverse through this entire array, right? Starting with I and j, and then we can find out all combinations. So for example, if we do I, and then we have this, right? Let's just do this, make this easy, right? And then we have I, and then we have j, right? And then we have I and j here. We want to move I in. We want to find out all different combinations that this array is able to yield. And then we have the array, right? The length. And then the area, length times height, right? And then since we have this case, we will then, can we compute all possible areas, then take the max, right? So we're looking at this, can we compute all possible areas and then take the max? Is that the most efficient way? Do we want to compute all possible areas and take the max? So for example, we're starting in here, right? And then we're moving in. Okay, so if I and j starts at the front of the array, it's not intuitive, right? It doesn't work because we are not using the max length. So by starting I and j on opposite ends, we are able to maximize the length of the container, right? So we started off here, and then now that we have the max length, we want to max height. Okay, so essentially when we are having this, we want to move I or j because they didn't say that the array is unsorted. So either we have choice to move I plus 1 or j minus 1, right? And this choice depends on the area. Yeah, great. Yep. So we must shrink this thing such that the area is maximized. Okay, so we're looking at this I 18625483937, right? And then we want to shrink this I, or we want to increment I or decrement j. Let's formalize this, right? Let's formalize this portion. The smaller one will form the height, i.e. height hold on, max min of I, like that. Right, so we want this, let's shrink this down. Okay, and then at any point in time, when we are at the exterior, we want to shrink the height. We want to ensure that the height is as maximum as possible. So assuming that in this case 1857, you have 1 and this, correct? And then what we want to do now is we want to increment I. You just want to return the maximum amount of water, right? 49, because it's do section 49, this is 7 times 7, correct? Yep. And in this case we have 0, 1, 2, 3, 4, 5, 6, 7, 8. 8 minus 1, 7, 7 times 7, correct? Yep. Times is will there be a case where, because every move I plus 1 or j minus 1 decrements area by 1 cm squared, 1, right? but height increase is unbounded. So this makes sense, right? So we want to shrink it down, decrement height slowly, and find the maximum height. So let's start. Okay, let's just look at this. So we have 0, 1. So in this case, 1 and 1 here. Okay, let's just immediately. I'm pretty confident this is this solution. We have an ON solution 1 to 7. We are just doing a 2-pointer approach, comparing them and shrinking them in, so it's a 1-pass linear algorithm. Yeah, this should be it. Yeah, let me just take a moment and I'll be right back. Try to wrap this up. So basically we're looking at this and we're shrinking it down, essentially forming the largest area by maximizing the height. So we are essentially maximizing the length of the container. I mentioned this here. Yeah. Okay. So let's just go right ahead to do this. Ij equals to 0, length of height minus 1, right? Once we've initialized this, we want to have two variables, height, smallest height, right? So we call it min height equals to min height I and height j, right? And then we have the length equals to j minus I. Area equals to min height times length. Right? Let's see if we can do this while I is less than j, right? We want to compute this, and then we have a max area equals to 0, and then we have this, and then if area is bigger than max area, max area equals to area, right? And then we want to return max area here. Okay, this is the first draft of my solution. Let's take a look at it. We have Ij equals 0, 0, length of height minus 1. This is 7, right? We start with I7, 0. When I is less than 7, we want to increment this, right? Let's do this once. And then when I'm here, what I want to do now is I want to, depending on area equals to max, I want to compare the area, right? How to determine whether or not to move j back or I forward? Yeah. You want to see whether or not we can increase the min height, right? If in if height plus 1 we want to make sure that it's increasing if it's bigger than I of I. Essentially, if height is bigger than height I, we want to increment I plus 1, right? No, we're looking at this in the wrong way. How do we know to increment I or to decrement j? How do we know to increment I or to decrement j? Initially, I'm starting off like that, right? How would I know for sure? If I increment I all the way, hold on. If I do this like that, and then with I, and then I decrement this all the way, I will be able to get all the different sizes of containers from here to here. But then that would take a double for loop, which I'm pretty sure is not the solution. In order not to do not to make the solution this way, I need to make sure that I can decrement or increment I in a linear fashion. So looking at this, we kind of need to tweak the solution such that if area is this, and then we have the area minimum of 2 heights. If I So initially, if we start off with I1 and 7, right? Essentially, even if we decrease 7, right? We decrease j, decrement j to 3, the total area would still increase, so the algorithm wouldn't work. But the question now is, how would I know to increment I rather than decrement j? Is that through the area of the resulting area? Right, so we have a height of I can be a very, very big number, right? I can always have, for example, 100 here and 100 here, and then we just take 100 times 1, it would still beat anything in the middle. So this is still pretty tricky. I'm not sure how to tackle this. We have min height equals minimum of height I and minimum height j. We have this, essentially this is the solution I have right now, but we're looking at this. Yeah, I guess there's no right solution here. There's no easy way aside from computing the entire area. The area is the source of truth. You can't do any shortcuts, right, with the length. So when I decrement A, I want to check out all the length. I could do a 2D matrix perhaps by populating all the length. So for example, the area of this to this, the area of this to this, area from this to this, area from this to this. But no. How do I know? There's no way I will know unless let's check out the hint. Simulate the problem. O(n) squared. Yeah, not efficient. I know that. 2 pointers, one to the left, one to the right. Always move the pointer that points to the lower line. Oh, I see. We want to do this. Alright. This is the key. We want to have to move the pointer that points to the lower line. Which means that I was thinking of this the wrong way, right? We must look at the pointer that points to the lower line. Because we want to maximize the area. At all times, we want to make sure that we want to have so essentially if height I is smaller than height j, right? Height I is smaller than height j, we want to move height I forward. Else so this is lower. The only way for me to increment this, so if you start off like that, the only way for me to increment this is if I have higher height. So I move in, right? I move into this, and then we are checking it out again, and then we see that this is lower. We'll move this in, move this in, move this in, move this in until we get this max area. Yeah, I think I almost got it. There's just some sort of confusion here. Area is equals to length times height. Yep, I got the idea. I was just a little confused towards the end. A little bit of a pity, but yep, that's about it. Thank you for watching.